I'm going to start by describing a feeling I'm sure you're all familiar with. The warm summer breeze gazes our skin and generates an immediate sensory response. Almost instantly, sensory fibers at our periphery send a signal along a nerve fiber towards our central nervous system, and we perceive the movement of the wind. However, in some conditions, this normally painless stimuli can cause adverse painful response. This is called mechanical allodynia, and it's a trademark symptom of neuropathic pain. Now, as a neuroscientist, the way I go about understanding mechanical allodynia is by asking the question, what goes wrong? Specifically, what are the molecular and cellular changes that differ from a normal condition and a mechanical allodynic condition? Only by understanding these changes can we think of ways to reverse the mechanical allodynic effects back to the normal conditions so that we can alleviate some of the pain felt by the patients. Now, to begin, I want you to think of a neuron as a miniature electrical device that receives thousands of inputs from upstream neurons. And this neuron will take these inputs and sum them up, and if it reaches a certain threshold, it will send out its own output signal to further downstream neurons. This intricate biological network is comprised of millions of different pathways and components. This is what makes isolating for one specific subset of neurons to be exceptionally difficult. Now, in my lab, we are focused on studying mechanical allodynia, and we have been able to find a specific pathway that connects touch inputs to pain projecting neurons. However, in between these touch inputs and pain projection neurons, we have a gatekeeper neuron. And under normal conditions, this gatekeeper neuron is inhibitory and it keeps the gate closed so that touch inputs can't reach pain projection neurons, so we don't perceive pain depending on light touch. These gatekeeper neurons are connected to a connector neuron that further downstream connects to a pain projection neuron. And because this gate is closed, there's no signal sending to the pain projection neuron. However, in neuropathic pain conditions, this gate is now open, so depending on touch input, the connector neuron will then communicate with further downstream neurons that communicate with the pain projection neurons and activate them. So that's why patients with mechanical allodynia feel pain depending on light touch. So our theory is that if we're able to close this gate again, then we'll prevent the touch inputs from activating further downstream connector neurons and then activating the pain projection neurons at the end. So another thing to note is that neurons communicate through signals, and these signals are fired at different frequencies. So we ask ourselves, is there a way to find the optimal frequency range of firing so that these gates can remain closed and we can help alleviate some of the pain that's felt with mechanical allodynia? And I present to you today a recent advancement in pain research that's based off the idea of precise control of a specific subset of neurons. Essentially, with this tool, we'll go through the pain projection circuit and either turn on or turn off the same subset of neurons. So with this, we can turn on the neuron and see what kind of behavioral effects it elicits. However, we can also turn off these neurons and see if we can revert back those behavioral changes back to normal conditions. So there are two components that are involved in this tool. The first is optogenetics. And optogenetics has been gaining widespread recognition and versatility ever since it was first used 30 years ago. Essentially, it takes light stimulation and converts it into electrical impulses in the neurons. So with this, we impose our external light frequency stimulation, and it would translate to the frequency of stimulation through electrical impulses in the neuron. And with this, we're able to modulate and impose frequencies that we decide on the neuron and see if it elicits any behavioral changes in our freely moving mice. However, we go one step further and we develop an additional adjuster to our switchboard. Now we have an off component. This is used with chemical inhibition, And we're able to combine both optogenetics and chemical inhibition in one tool to target the same specific neuron. And with this tool, we're able to see, to turn on the neuron, fire it at different frequencies, see the behavioral changes in the mice, but also see if we can reverse those behaviors using the chemical inhibition. And this elucidates the physiological role that specific neuron plays in the pain processing circuit. The potential of this tool to treat different disorders is extensive. Our hope is that by studying pain processing circuits at the level of isolation that lets us repair and engineer specific neurons, we're able to target and develop treatment modalities that are able to improve the lives of neuropathic pain patients everywhere. Thank you very much.